Electronic design automation, known more commonly as EDA, has played an important role in IBM for over 50 years. Part physics, part mathematics, part electrical engineering, and part computer science. This field brings theory and practice together to enable the creation of the most complex systems in the history of human existence. The IBM EDA team develops sophisticated software to speed hardware design and enables IBM to grow its technology leadership with each new computer system. While innovation in IBM comes in many flavors, hear the history of IBM EDA and some of the best examples of continuous innovation that matters. In the mid-1950s, the popular IBM 704 computer was used to document the design of new products. The vacuum tube computer used high-speed magnetic core memory, which replaced the electrostatic memory used in earlier machines. IBM was a pioneer in using design automation to evaluate Boolean equations to confirm that the 704 behaved correctly. Arguably, the birth of EDA in IBM occurred in 1958 when Case and Simek developed an application called Engineering Change Control. Less than 1 year later, Jack Kilby of Texas Instruments and Robert Noyce of Fairchild Semiconductor invented the integrated circuit, which unleashed 5 decades of explosive growth in microelectronics that is still going strong today. In 1963, IBM boldly introduced the System 360 family of compatible computers with a broad range of performance. These machines used a new semiconductor called solid logic technology, which combined a few transistors in a small ceramic package. With the increasing number of systems, the growing complexity of designs, and the introduction of new technologies, the need for design automation became clear. To meet the growing need for this fledgling science, IBM hired some talented upcoming engineers. These young engineers literally invented the EDA industry we know today.
I came into IBM as a mathematician, and I was doing kind of theoretical differential equations.
I want to work on software tools because I figured software was really the big problem.
I told him I wanted to be a logic designer. That was my objective for my career.
And I met a couple of people from IBM, and they invited me to come as a co-op to Yorktown.
We would sit in a graphics room and literally do circuit layout drawn on a screen.
I don't know anything about computers. I hate computers. And that's how I got into CAD.
During the time of the System 360, when integrated circuits consisted of a handful of elements, designers used a variety of sophisticated tools, including pencil and paper, breadboards, and X-Acto knives. This was the era of manual design.
Designers would use discrete components on a breadboard to try to predict the behavior of integrated circuits.
This was not any easier for physical design.
Designs could be drawn by hand. In fact, literally were drawn by hand on a piece of paper.
Or for manufacturing.
The way that the layout patterns were transferred into manufacturing was this sort of silk screening process where people would actually go with an X-Acto knife and they would cut out patterns and they would, lay them down on the silk screen and then kind of hold them up to the light, and if they looked okay, then that was good enough.
We would use punch cards sometimes for JCL jobs, or we would type in the JCL. I remember once accidentally punching a whole GL1 of a master slice, an analog master slice, to the wrong sysout class, and it came out in cards, a big box, which served me pretty well for note cards for 15 years.
During this time, however, a new tool emerged.
In addition to doing things manually, we could write lines of code and have those lines of code do parts of the design for us. So lines of code became one of the tools that we use to do circuit design.
For the first time, some work started, including a lot of IBM stalwarts like Brennan and Ho, and Rulli and Hachtel, where they tried to use a computer to predict the behavior of electrical circuits. There were two main problems they had to solve. They had to represent the circuits as ordinary differential equations, and then find a way to efficiently solve these equations. And IBM played a major role in the breakthroughs required for both of those.
We kind of reformulated how you solve circuits on the computer. And we had something called the sparse tableau approach.
Sparse tableau, and later modified nodal analysis, were two of the many IBM contributions to circuit simulation. Tools such as ASTAP from IBM and SPICE from UC Berkeley allowed designers for the first time to verify circuit performance before manufacturing.
Those ideas, we helped them a lot and put it into a program called ASTAP, which was in IBM and solving circuits for 25 years, I guess. I don't know.
To this day, every power, noise, or timing calculation that we do for every integrated circuit relies on techniques used in SPICE.
Building on the success of the System 360 and 370 systems, in the 1970s, IBM invested more in design automation. With the advent of large-scale integration, challenges arose between chip design and chip manufacturing.
The design environment at the time was such that there was design, and then they would pass the design over to manufacturing test. And manufacturing test created the test patterns and actually debugged them and tested the parts. And in 1971, this task force was formed, and the conclusion of the task force was that testability is the designer's responsibility.
This was a poignant moment in EDA's history, as it was the catalyst for the formation of the Test Design Automation Group that supported the designer's new responsibility. Innovation poured out of this group with the release of an automated method for testing logic after manufacturing.
So the next challenge, there was challenges going on both in the manufacturing test and in the system test area. Challenges in debugging the designs, both from a manufacturing perspective and also a system test perspective. So another group was formed, and this one Ed Eichelberger took the lead. And out of this came level-sensitive scan design. With a structured test environment, you're looking at just the logic from a sheer logic perspective. You actually knew how good a job you were doing, what percentage of the logic you were activating. And also key to all this was it enabled diagnostic simulation, right? Once I have these fails, where was the fail? How can I quickly get to the root cause?
LSSD, both for test and for debugging and diagnosing systems, has been very important in IBM, and it's a way that IBM has taken the leadership in the industry to be able to very systematically and completely test and diagnose and debug our systems.
During this time, new multi-chip packaging systems were being developed, including the revolutionary thermal conduction module. This led to another major advancement from the Test Design Automation team.
And the methodology at the time was called chip-in-place test. So what they did was around each chip was an array of test pads. And the tester would come down and really test each chip individually and isolated. Paul Bardell was, took a big step, and he formed the self-test steering committee to work out what do we do, how do we do it, what is our plan, we got a problem, we need a solution. And out of this came built-in self-test. So now we've moved the generation from the tester, so now we're moving it into the chip itself. So we have built-in self-test both for logic and arrays.
As LSI was growing through the decade, a new class of tools appeared: verification. Used to check the correctness of a design, there was both formal verification.
In 1978, IBM's pioneering team of Smith, Banson, and Halliwell developed the world's first combinational equivalence checker, SAS, for static analysis system. The ability to exhaustively verify the correspondence of two design versions marks an evolutionary leap in design productivity and circuit robustness, which later spread throughout the semiconductor industry.
As well as cycle simulation.
IBM has a rich history here in simulation-based verification, dating all the way back to the 1970s, late 1970s. The one unique feature of IBM's verification approaches has always been that we have matched our design methodology very closely with what works well in verifications. Like many other things in IBM, the simulation methodology that we use originated with the mainframe team in Poughkeepsie. BDLCS was a language before there were other RTLs. We went from our own proprietary RTLs to industry standard formats and enabled our tools to work with the industry standard formats while still keeping the unique features for scalability and for performance.
With these and other successful EDA innovations, there was one critical ingredient.
The close integration between the designers, between the design automation software, between manufacturing. I mean, it needed to be a very close, intimate relationship between these groups for these methodologies, which were critical for IBM to come to life.
Innovations in design automation, device technology, and system architecture came together for the release of the IBM 3081 in 1980. Then, cycle simulation did something no other EDA software ever did.
They took that 2-year window and took it down to 6 weeks.
It made the jump from software to hardware, 20 years ahead of its time.
The reason IBM, I think, was way ahead of the curve on this one is because early on, IBM recognized the need to do cycle simulation because it enabled, for example, if they could get the designers to write the behavior one time in the cycle simulation language, which at that time was called BDLCS. And they had all of their design methodology structured around cycle simulation. They had timing, they had synthesis, they had static analysis, all these things, and cycle simulation is just sort of at the core of that whole methodology. What the hardware accelerators do is they manage to stay 100 to 1,000 times faster than what they can do in the software, which enables them to do a lot more testing much earlier and get a much better quality of the design when it's manufactured.
Ideas from IBM researchers, including John Koch, Richard Baum, and Monte DiNao, went into early machines such as the Los Gatos Logic Simulation Machine and the Yorktown Simulation Engine. These culminated in a machine known as Eve.
Then really moved from research into production with the generation of the engineering verification engine, the Eve machine.
It was done in Endicott starting in the early 1980s, and they went online in production use in about 1985. Most of them got put into Poughkeepsie, which was the main driver for this.
Ultimately, that led to the concept of the Eve 2 machine. And it was at that time that I joined IBM, and my first project was with the Eve 2 development team. And what's been incredible to me, seeing the teamwork and the collaboration across these organizations, taking these ideas again from research into this very large-scale production.
And so I remember, for example, prior to the machine that was used, and I don't remember exactly which one it was, but the machine which they had before the Eve machine, it took them 2 years to bring up the working hardware, and they had tremendous costs in terms of engineering, hardware that had to be scrapped, impact on schedule. It was not quite a disaster, but it was a really, really, really bad bring up. The first machine that they used Eve on, they took that 2-year window and took it down to 6 weeks.
During this time, CMOS technology was also emerging to displace bipolar technology in IBM's chip designs. This continued the relentless pursuit of Moore's Law and posed new challenges for EDA.
In the 1980s, the industry started to make digital circuits with a level of complexity that had not been seen before. The problem with these digital circuits is that they have an enormous number of paths through the circuits, millions or even billions of paths. And it became impossible to verify the timing of all these paths with SPICE-like techniques. IBM invented static timing analysis, published first in 1982 by Hitchcock, Chang, and Smith, to implicitly cover all the myriad paths through a digital circuit. Although these techniques took a while to take hold, it is fair to say that the digital revolution would simply not be possible without static timing techniques.
In the late 70s, early 80s, IBM was way ahead in hardware design methodology. They had cycle simulation, which gave them really fast verification. They had static timing analysis way ahead of everybody else. They had formal methods to prove the two were equivalent, so you didn't have to do gate simulation, automatic test generation.
I think that the time was exactly ripe for logic synthesis. There had been many years of work on PLA optimization and minimization and other kinds of logic optimization, but the key thing that happened in the early 80s was the invention of cycle simulation. And cycle simulation required the designers to put a high-level specification of the design in.
But designers were very frustrated. They felt they had to design the chips twice. They had to provide a behavioral specification and flowcharts, and they had to provide a structural specification of how to interconnect the circuits together. So they weren't happy. So the question was, could you try to generate the implementation from the original specification? And Bill Joyner joined me, and we sat down and we tried to figure out, could we get from one to the other by a set of simple transformations? And it turned out we could.
So the designers had to do a high-level specification, which was ideal for synthesis, plus we had an automatic checking tool that could do a Boolean comparison between the input the designers put in and the results of synthesis that would really encourage people to believe that the results were correct.
So Poughkeepsie management thought maybe they should try this on something real, and coincidentally at that time there was a 3090 project that was understaffed and behind schedule, and they were supposed to do a 100-chip TCM.
The 3090 was a different technology, so it required some changes to the code. It was a much more complex technology. We had to do a lot of upgrades, and then we did I think a dozen or so chips to see that it worked. And at that point, the 3090 project committed to synthesizing an entire TCM worth of chips. And that was a little bit of a shocker, since it had been run on 10 parts, and all of a sudden we're in the product mainstream having to do 100 chips.
So there's a lot of chips, and they said, let's try it. So we worked with them, really intense. We were on the phone every day with them. We would go to Poughkeepsie every week, sit down with them, and they had assigned John Gerby and Jim Eadie to work with us in Poughkeepsie.
It was a wonderful experience in terms of the collaboration with the design team, who were really, really supportive and really gave good suggestions and a lot of help to get it done. And in the end, we did 90% of the chips on that TCM.
While IBM has consistently been a leader in using computers to capture, check, and map design layouts to masks, it was the decade of the 80s when IBM EDA rolled out first-of-a-kind software tools for release to manufacturing.
So release to manufacturing refers to applications that kind of happen at the very end of the design process as the design is being handed off to manufacturing. These applications usually involve looking at layouts, which are the physical patterns that ultimately will appear in the silicon. And there are sort of two flavors of these kinds of applications. There are some which will check the layouts for compliance with certain manufacturing rules, and then there are some that actually transform the patterns in the layout. A school teacher, an elementary school teacher named Glenn Weinert in Burlington, Vermont, ended up working for IBM and wrote a program called Pelican, which was the first program to kind of transcribe the design data, or the layout data coming out of design, into the language which is used by the photomask generation tools. In the early part of the 80s, the kind of the layout to silicon patterning process was sort of WYSIWYG. You know, what you see is what you get. The patterns in the layout data resemble the patterns on the photomask, and those resemble, in turn, the patterns which are on the silicon. The mask writer, which uses a focused electron beam, started to exhibit characteristics where writing in a certain part of the pattern would actually influence what was happening in other parts of the pattern, so-called proximity effects. And this led to the development of a program called the Hantus post-processor, or HPP, which was specifically designed to be able to compensate for those proximity effects, subtly changing the shapes so that ultimately the photomask would appear as the layout had indicated. The big concern at that time was there was this future chip, a 256 megabit DRAM chip. And this was colossal for the time. If you extrapolated from runtimes that existed, the expectation was it was going to take 1,000 hours to check one of these 256 meg DRAMs. Glenn Weinert, the former elementary school teacher I mentioned before, came up with an idea that sort of exploited the aspect of VLSI designs that typically there was a lot of repetition, a lot of substructures that were identical, a so-called nested hierarchical structure. And what they did was to develop a means of processing those kinds of designs that took advantage of that repetitive nature. Moving from the so-called flat checking method, where you looked at every shape, to this nested processing method, ended up sort of speeding up the process for checking these DRAMs by a factor of about 100.
The last 20 years have seen some remarkable changes in device technology. The 90s saw the end of scaling, and EDA stared right at the laws of physics.
After a while, the wire cannot keep up the scaling with the devices. So that means a lot of delay now reside in the wire and not on the device anymore.
ASICs actually moved to the, I believe it was the SA12 technology, but at that time, the first generation, we had an aluminum backend, we didn't have the copper backend yet. So suddenly at that switch, the wire delay just made a huge jump, and we noticed that basically doing synthesis without placement was pretty much impossible.
Our tools are usually adopted by the server division first, because servers run at a much higher frequency, so usually they are much willing to try something new, or they actually need something new usually first. But the difference here is they do the design in a very methodical way, so they partition the big units into tiny little macros, so they do the floor plan placement very, very carefully, so you do not see the problem of the long wires quite yet.
So then in March, some of the first chips started to release to layout, and indeed they started to find the interconnect problems. So there was a desperate call from Burlington. Okay, do we have a tool that can do something here? So we quickly patched the version of CPlace and Bulldozer together. So we luckily had this concept and prototype tool called Nutshell, which allowed you to basically link a lot of EDA applications together. So that allowed us to basically take the timer, take CPlace, take Bulldozer, and at least put them into one Nutshell process, which almost made it look like one tool, which was the very early version of PDS that got released at that time.
And we used to build these big monolithic systems that did one thing and had 87 different inputs. And if you wanted a new feature, you stood in line, you put it in there and it got planned. But through the 90s and 2000s, the sort of modularization of function, when I think about the timing functions, the placement functions, the circuit functions, all became modularized and then extensible.
Slowly, as the servers moved into very high frequency, where the distances the wires can travel for a given cycle time became smaller and smaller, even their smaller macros were not sufficient to ignore the wires anymore. Well, there's only so much you can tweak the system, and well, as it always happens, they came around and said, this is a disaster, do you have something to solve it? And luckily we had something that we had been working with the ASIC folks on, where we merged Bulldozer and PDS together, and that paradigm was called PDS RTL, which we enabled for the server design.
So we were able to include some of the routing work that we had been doing with Cadence in the MAR project, pull that into the optimization flow, and build a new tool called Rapids, which really helps to battle some of these late deep submicron effects. So I think what you see is that the good thing is at IBM we have a lot of great components for each of the tools, and are able to integrate them well together in a timely fashion, kind of to deliver design flows while the technology needs continue to progress through the decades here.
We have to worry about what used to be, third order effects, noise, coupling, reliability. The flexibility of actually having to adapt to those technology transitions is really, it really shows the mental flexibility of the organization.
So as of today, we have synthesis, placement, and routing fully integrated into our physical synthesis suite. Today, physical synthesis is used in every chip design product we make for both our processor designs as well as our ASIC design systems.
We have on the order of 20,000 CPUs running 24/7 across IBM server installations to do chip verification jobs.
Today, there are something like 60 machines, individual machines, in use in the IBM Corporation. That's a big investment, and for IBM to continue to make that investment after all these years, third generation of this latest family of machines, they wouldn't justify the cost for that if it wasn't a highly effective tool for them to use.
Today, the modern day release to manufacturing applications typically run on cluster farms with 1,000 to 10,000 cores and run still for a couple of days. So in addition to release to manufacturing facilitating the development of server technology, now server technology is increasingly being driven by these applications.
What do we need from the tester? We got our BIST on board. So we need a seed, we need a weight set. All we need is a reference clock. We don't need a high-speed clock. We don't need a lot of tester memory. We need power. So we're able to test these very advanced, very state-of-the-art chips with very cheap test equipment.
In the remarkable evolution of this industry, we have faced difficult technical problems at various junctures. IBM was at the forefront of coming up with solutions to these problems that helped not only IBM but the industry at large. No other company or university can lay claim to such an eclectic set of breakthroughs.
An EDA person has to have pretty good design skills, but also has to have the math and computer science skills to kind of go with it.
You can find broad thinkers that really understand the whole problem end to end, work with the design teams, understand technology, or you can find really deep thinkers where you can go just, hey, can you figure out how to address this one technical problem?
What I see at the conference is really displays IBM's reputation in the industry as an innovator in EDA tools.
The biggest lever we have is in algorithms, right? And so the CAD people are going to become people who know that stuff and can actually optimize, for increasing variability, increasing, device counts, etc., are going to be more in demand. And more, we're going to need to optimize at a system level, or even at a system and software level as we co-optimize those things. And I tell you, the skills that we have in this organization in terms of understanding how to mathematically formulate things, optimize them, and get data in and out from the real world, so key. So I really think it's a good time to be in CAD, and I think that the men and women in this organization should be really proud about what we've done to drive the company's the company's growth. Getting to 100 years, it wouldn't be anything if we weren't able to make these chips. It really wouldn't be.
IBM always hired the best people and continues to hire the best people in design automation.
Challenges await for the IBM EDA team. Taking advantage of its rich history and experienced workforce, EDA will offer substantial contributions to IBM hardware development and IBM's innovations of Smarter Planet, business analytics, and cloud computing. The EDA journey has been an enormous success story, and this story will continue for years to come.